Hello everyone, welcome to my YouTube channel ECE Scholastic. I am Jasmine. So today we are going to see session 8, that is problem under mechanical rotational system. So in the previous session we have discussed problem under mechanical translational system. In today's session we are going to solve a problem under mechanical rotational system. So before solving the problem, let's recall the formula related to mechanical rotational system. So the elements of mechanical rotational system are moment of inertia, spring and dashpot. Here input is torque T and output is angular displacement theta. So let's see the formulas related to each element. The first element is moment of inertia. So the formula related to moment of inertia is Tj is equal to J into d square theta divided by dt square. The second one is dashpot. The formula related to dashpot is Tb is equal to B into d theta by dt. If we are having two angular displacements theta 1 and theta 2, then the formula for opposing torque is Tb is equal to B into d by dt of theta 1 minus theta 2. Next is a torsional spring. Here the formula related to opposing torque is Tk is equal to K into theta. Similarly, if you are having two displacements theta 1 and theta 2, then the formula is Tk is equal to K into theta 1 minus theta 2. Now let's solve a problem. So the question is, write the differential equations governing the mechanical rotational system shown in the figure and determine the transfer function of the system. So we need to find what is the differential equation and we need to find what is the transfer function. Correct? So for a mechanical rotational system, torque is called as the input and angular displacement theta is called as the output. Correct? So on analyzing the diagram, we understood that it has two moment of inertia J1 and J2. So if there is two moment of inertia, if there is two nodes, then there must be two displacements. So the displacement related to J2 is theta and we don't have any displacement related to J1. So we are assuming a displacement related to J1 as theta 1. Okay. As we are familiar with the steps, we can solve the problem directly. So the solution is, so what is our step 1? Our step 1 is identification of number of nodes. So here the moment of inertia are considered to be nodes. Okay. Since we have two moment of inertia J1 and J2, we can say that number of nodes is equal to 2. What is our step 2? Our step 2 is free body diagram for each node. Since we are having two nodes, we will be having two free body diagrams. So let us draw the free body diagram for node 1. So J1 represents our node 1. The elements connected to J1 is K alone and we have an applied torque T. Okay. So the free body diagram for node J1 is, okay. So we have an applied torque whose direction is towards downwards and we have assumed a displacement theta 1 whose direction is also towards downwards. Therefore, the direction of opposing force will be towards upward. So the element connected to J1 is K and J1 also exerts an opposing torque. So therefore, we can write the opposing torques as Tj1 and Tk. Okay. Similarly, for node 2, the elements connected are spring K, dashpot B. Correct. For node J2, the elements connected are spring and dashpot. So the opposing torques are Tj2 and Tk, and one more is there, dashpot, that is Tb. Okay. And it has a displacement theta. Okay. So what is our required transfer function? Required transfer function is here in the diagram itself it is given theta as the output. Therefore, the required transfer function is theta of S divided by T of S. Okay. This is our step 3. Our step 3 is writing differential equation. So for node 1, I am going to write the formula, that is Tj1 is equal to J1 into d square theta 1 divided by dt square. And K is situated between the two nodes J1 and J2. Therefore, it takes the displacements theta 1 and theta. Correct. So, the formula for Tk is Tk is equal to K into theta 1 minus theta. Now, let me write for the second node. Therefore, Tj2 is equal to J2 into d square theta divided by dt square, and Tk is equal to K into theta minus theta 1, and Tb is equal to, B is applied to node 2 alone. Therefore, Tb is equal to B into d theta divided by dt. This is our fourth step. Our fourth step is apply Newton's second law. So, what is Newton's second law? Sum of applied torques is equal to sum of opposing torques. Okay. So, for node 1, we have an applied torque, correct? For node 1, we have an applied torque and we have the opposing torques Tj1 and Tk. So, we are going to write this as T is equal to Tj1 plus Tk. So, what is Tj1? Tj1 is nothing but J1 into d square theta 1 divided by dt square, and Tk is nothing but K into theta 1 minus theta. So, I am taking this as equation number 1. So, I am going to apply Newton's second law for node 2. So, for node 2, we don't have any applied torque. We only have opposing torques, correct? So, applied torque value is 0. The opposing torques are Tj2 plus Tk plus Tb. On applying the values, 0 is equal to J2 into d square theta divided by dt square plus K into theta minus theta 1 plus B into d theta divided by dt. I am taking this as equation number 2. Now, what is our step 5? Taking Laplace transform. So, I am going to take Laplace transform for the first equation. Okay. So, what is Laplace transform for first equation? T of s is equal to J1 s square theta 1 of s plus K into theta 1 of s minus theta of s. So, from equation, I am going to take theta 1 of s as a common factor. So, theta 1 of s into J1 s square plus K minus K into theta of s. Left side is T of s. I am going to take this as equation number 3. I am going to apply Laplace transform for the second equation. So, the second equation is this. Therefore, 0 is equal to J2 s square theta of s plus K into theta of s minus theta 1 of s plus B s into theta of s. So, from this I am going to take theta of s as a common factor. Therefore, the answer is theta of s into J2 s square plus K plus Bs minus K into theta 1 of s. Our left side is 0. Okay. I am going to rearrange this expression, that is theta of s into J2 s square plus Bs plus K minus K into theta 1 of s. Left side is 0. So, we need to find the transfer function which is theta of s by T of s. But in the question we have two displacements, that is theta of s and theta 1 of s. So, I am going to find theta 1 of s in terms of theta of s from this equation. Okay. So, now K into theta 1 of s is equal to theta of s into J2 s square plus Bs plus K. So, from this I am going to find what is theta 1 of s. So, theta 1 of s is equal to theta of s into J2 s square plus Bs plus K divided by K. Okay. I am going to take this as equation number 4. So, our step 6 is we need to find transfer function theta of s by T of s. So, in order to find the transfer function, I am going to apply the value of theta 1 of s in T of s equation. Okay, which means substituting equation 4 in 3. Okay, so this implies T of s is equal to, okay, theta 1 of s. So, instead of theta 1 of s, I am going to apply this value. Theta of s into J2 s square plus Bs plus K divided by K, okay, multiplied by J1 s square plus K minus k into theta of s. Okay. So from this I am going to take theta of s as a common factor and I am taking a common denominator k. So my answer is j2s square plus bs plus k into j1s square plus k minus k square. Okay. This is t of s. Okay. I need to find what is theta of s by t of s. So I am going to find what is theta of s by t of s, which is our required transfer function. So this is equal to k divided by j2s square plus bs plus k multiplied by j1s square plus k minus k square. So this is my required transfer function. I am taking this as equation number 5. So that's all about the problem. Hope you understood the problem. Thank you for the patience. If you have any queries, please mail me. Don't forget to like, share and subscribe. Thank you.